Okay, guys, so we're going to get into angular kinematics of human movement. Remember, kinematics is something that we can measure with a measuring device and a stopwatch. Fairly simple. And then kinetics is something that we are talking about forces being applied. And now we're going to start to move into angular movement. Angular movement applies a little bit more to the human body because our joints work around angles. So our body parts that are moving around fixed points, also known as our joints. Then here's your learning objectives. Good idea, good stopping and starting points before studying for a test. Which of these are you really comfortable with, and which do you need to go back and review more? Angular movement is something that can be easily measured on the human body with a very simple tool that you're all familiar with, a goniometer. When we're measuring joints, one of the big things that is important are references. A lot of times when we measure joint angles, we reference the anatomical position, so just having hands supinated, laying flat, and that's usually a good reference point when we start talking about angular movement. So a fully extended joint, like a fully extended knee or a fully extended elbow, a lot of times will be referenced as 0 degrees if the units that we're talking about are in fact degrees. It doesn't necessarily have to be that way, that you can say that's 180 if you would like. It's just really important that between, let's say we use 180 and then you end up at 90 degrees, you just have to understand that the angular movement between those 2 points was 90 degrees, right? So you have to just know how to measure between wherever you're starting and stopping point is, whether you want that to be 0 degrees when a joint's fully extended or you think you like that as 180 degrees. And a lot of times I will just tell you that. I will tell you that from the get-go. Body segment orientation. So really what this has to do a lot with is the body laying flat? Is it standing upright? And if somebody is standing upright, okay, how do we reference where flat is, right? So where are we measuring from? And a lot of times it's the horizon or like something flat behind the person, like the sky or the track or a sidewalk or a treadmill or something that's flat that we can reference the start from where angular movement occurs. So a lot of times we'll measure different joints at the same time. So if we are using that horizontal reference in the horizon to measure the angle of the trunk while someone's running, we can do that, and then we can measure the angle of the knee where our reference is anatomical position. So anatomical position would have the knee fully extended, like imagine someone laying flat on the table. So if we used 180 degrees to start, or let's say we used I guess 0 degrees, this person would have passed 90 degrees at the knee, if that makes sense. The instant center of rotation is just that very, very center of the joint about which everything is rotating at any one time. So the instantaneous center of rotation is the very center of the joint about which things are rotating. So now we'll get into angular kinematic quantities. These quantities are the exact same quantities that we measured linearly, but there are some different units that we're going to use and some different variables that we're going to use to describe them. So the first one is angular displacement, the change in angular position or orientation of a line segment. So we measure that, compared to where it started. It's a vector equivalent of angular distance, right? And it is measured in a few different units: degrees, radians, or revolutions. Obviously, a good example here would be we're looking at a dumbbell curl. Angular displacement at the elbow would be 0 because the forearm moved angularly and then returned back to its original position. Displacement is A to B, so if displacement here is A to B back to A, that would be 0 displacement. Now, if we want to compare displacement to distance, again, they are vector equivalents of one another, meaning that we're measuring angular distance and displacement. It's just the description of them that identifies which we're talking about. So angular distance, if the forearm continues just to flex and extend, flex and extend, flex and extend, we could measure distance infinitely. Displacement, however, always identifies A to B. So displacement would go so far and then always return to 0. So making sure we understand the difference between angular displacement and angular distance. Angles are measured in a few different units. One of the ones you're most familiar with, I'm sure, is degrees. So angular degrees, 90 degrees at a right angle. Now, this is where things can kind of get confusing sometimes. I tend to prefer, usually when I'm measuring joints, if a joint is fully extended, I tend to think of that as 180 degrees. Your book talks about it being 0 degrees, but that gets really confusing for me because when we actually talk about degrees themselves, like a goniometer, a lot of times it'll be 180 degrees if a joint is fully extended. Like if somebody's trying to rehab their knee after an ACL tear or some sort of surgery at the knee, a lot of times the goal for the physical therapist will be to get that knee as close to 180 degrees as possible, not 0 degrees. Again, it really doesn't matter as long as you know where your point of reference is, and one of the most popular units that we use more often than not is degrees. Another unit that we use when we're talking about angular movement is radians. Some of the equations in physics and in this class that we'll use require that you use radians. You can't use degrees. Now we can always get from radians to degrees. 1 radian is equal to 57.3 degrees. So we can always transfer back at the end. You're like, what is that in degrees? Okay, I've just done some calculations in radians. That doesn't make a lot of sense to me. I'm used to using degrees. So you can always convert back to degrees. Just understanding radians kind of helps bring a larger picture into it, I think, because 1 radian is, if we know that the radius is the distance from the center of the circle to the outside of the circle, well, if something is rotating 1 radian, it's rotating around the circle the same exact distance that it is from the center of the circle down to the side of the circle. So 1 radian is the same distance around the circle as it is to the center of the circle. Another thing that we need to keep in mind, especially when we start talking about relationships between linear and angular movement, is this concept of tangential movement. And usually, well, always when we say tangential movement, we mean linear movement, not moving around a curved path. We can look at a curved path and we can describe linear movement on that curved path with this concept of tangential linear movement. So if we have a circle and we're moving around the circle, we might have radial components where things are moving towards the center of the circle, and we might have tangential components where things are moving across the curved surface of the circle or a curved path. So angular movement, or moving around a circle, has two different components, and one would be the linear component or the tangential component, the flat linear component that skims across the surface of the angle or the curved path, and then the radial component, which is what's going inside the circle, which we'll talk about later. You're probably more familiar with tangential movement than you think. If you've ever been on a road or a trail or something, hopefully you don't do this in your car, but if it's a really curvy path and you might pop into your head, well, it's going to be a lot easier for me to get from point A to point B just by taking a straight line on these curves instead of hugging the curves. In endurance sports like cross country, if you're running, a lot of coaches would say if you're running on a really curvy trail, don't necessarily hug the curves. You're going to take a longer path if you hug the curves than if you just take a straight point between the parts of the curves, and that would be tangential linear movement. So to kind of bring it back to the different units that we might use, again, degrees and radians are going to be the most that we use in this class. We don't usually refer too much to revolutions. I mean, revolutions is probably the simplest way to do it, and it's harder to calculate using a calculator. One thing that I want to bring up here, if we are using radians and degrees and we're flip-flopping back and forth between the two, a lot of calculators, you have to go into your settings and make sure that the calculator is calculating in degrees or radians, especially if it's like a TI-83 calculator. So keep that in mind. If you're getting really super weird answers and you know they're not right and you're doing the calculations correctly, your calculator might be set to degrees or radians, so get it into the one you want. Okay, so I said earlier that references are really important, and we talked when we were talking about linear kinematics and linear kinetics, we used a signage every now and then to describe movement in the x and y axes. Is it x negative? Is it y positive? Angular movement is no different. We need to understand which is positive and which is negative. For the most part, depending on how you're watching someone, and now if I was watching this person from the side or if I was watching this person from the front, I would have to essentially just kind of put a clock face on them. And for this example, counterclockwise movement is positive angular movement. Clockwise movement would be considered negative angular movement. Now, if you were looking at someone and you were looking at the right side of their body and they were raising their arm and lowering their arm, raising the arm would be counterclockwise positive movement. Lowering the arm would be clockwise negative movement. If they turned around and flipped around and you're now looking at the left side of their body, that would switch, right? So keep that in mind, that depending on what side of the body someone's using and how you're looking at them depends on if you're going to describe the angular movement as positive or negative. Okay, so now we get back into some terminology that you're familiar with, just applying it angularly. Angular velocity. So we're still using displacement as a description of, so the change in angular displacement over a period of time. We have a couple different symbols here that are going to pop up quite a bit when we start talking about angular components of movement. So angular displacement usually is denoted with a theta or a circle with a horizontal line through it. And then angular velocity is usually almost always denoted with an omega or an italicized lowercase w. Now, we've explored quite a bit about linear movement. Linear and angular movement are inherently linked to one another because if something is moving angularly, we can also describe certain parts or segments and how they're moving linearly as well. So if something is moving around an arc and it's a certain length or radius away from the center of rotation, we can describe how that relationship works with reference to the linear movement of whatever we're tracking. So when we look at an arc length, we can really describe that as the linear distance that something's moving, in kind of a curved path. And we know that the further something away is from the point of rotation, the further the arc path that it's going to take, or the longer the distance that it will take around a point. So let's look at that with a picture. It'll bring it together a little bit. So we can see that if we look at this linear distance or arc length, which we describe as S, and the radius, just take a certain point away from the center of rotation. So S1 is obviously much closer to the center of rotation than S2 is. And when the body, the segment starts to rotate, if S2 is a longer radius away than S1 is from the point of rotation, then there's going to be more linear distance traveled, which is S2. Now, one thing to really kind of key up on here is using these symbols. So we talked about how theta, a circle with a horizontal line through it, represents angular displacement. So you might be thinking, well, that's theta. Why does that say angular distance? Well, that's not a theta. That's actually a phi, P-H-I. Some might pronounce it phi. But it's you pronounce it phi, P-H-I, so a circle with a vertical line through it. So however much angular distance you cover, however far away a point is on a straight line like a radius, will describe how far that point travels. So we can see that if we have something with a very large radius, it's going to travel further on a path than something with a shorter radius. And there are lots of different ways I can describe this relationship. So the arc length, or the distance, the linear distance something traveled, can be described as the product of the radius and the angular distance. The change in arc length can be described as the change in angular distance multiplied by the radius. If we were wondering about the angular distance that was covered, or phi, we take the arc length and divide it by the radius. And that could be a good question on a calculation exam. And we can use that relationship to describe how different points on the same line are related. So if we know the arc length and a radius of some point on a line, and we're wondering about the radius, how far away another point is, we can use this relationship, and we know that if we take arc length 1 and divide it by its radius, that will be equal to arc length 2 divided by its radius, because they're on the exact same segment that's rotating around the exact same point. And if you want to put it on the human body, we can say that point around which these things are rotating in this picture could be the elbow, and this could be the forearm. And it could be S1 could be the wrist, and S2 could be the fingers. Now, I mentioned earlier that units are important, and a lot of times we will use degrees. But in instances where we're talking about angular distance, or phi, the circle with the vertical line through it, you're going to have to use radians. We can always transfer back to degrees at the end, right? But for use of these equations, you have to use radians. And you have to use the same units of length between S1 and S2 and the radius. If you're going to use meters, you have to use meters. You can't use meters and inches. So to kind of bring it back to a practical application, why do we use staggered starts in track and field? We're going to think about that for a second and apply the information that we just talked about. So if we have runners and they all started on the exact same starting line, lined up shoulder to shoulder, well, the people on the very outside, they would run further because they are further away from the point of rotation. The point of rotation would be just the center of the field. It wouldn't be fair because they are on a point further away and they would travel a greater arc length. And to make up for that in sports, they start them staggered so that by the time they hit the curve, by the time they come through the curve, they're all equal. Another experiment, you could actually try this yourself if you wanted to, that describes the relationship between how far away something is on a radius and the arc length that it will travel. Is if a rotating stick struck the balls at the exact same time, obviously the ball that's closest to the axis of rotation wouldn't travel as far as the one on the furthest point away. Okay, so here's an example. I would encourage you not to move ahead, to try this out on a piece of paper and then move through the problem using the equations that I've given you here. So it's about golfer and putting and arc length of travel. Go ahead and read the question, practice it yourself, maybe pause the presentation right here and give it a try. Best way to take a stab at this problem, if you don't have another system that you're really comfortable with for solving these problems, is to go back to the guess method that we talked about a few times in class. What do we have? What have we been given? We've been given the arc length of the hands, the radius of the hands, radius of the putter. We want to know the arc length of the putter. What formulas can we use? We have a couple that we can use and that we can rearrange to use how we would like. And then if we know that we have an arc length and its radius, and an arc length, another arc length and its radius, then we can do the math, right? So leave that problem to you to put together on your own. And if you have questions about getting the correct answer, obviously check with me. Fairly straightforward. As I said earlier, this applies directly to joint movement. Right, the fingers are going to obviously move in a larger arc length than the wrist or the forearm will if we're measuring points away from the elbow rotation. So we just covered some relationships between linear and angular distance, arc length of travel, linear, angular distance, radius of a point on a rotating body. Now we're going to look at relationships between linear and angular motion, specifically velocity. Linear velocity versus angular velocity. And remember, angular velocity is denoted by that omega, that lowercase italicized w. We know that linear velocity, or tangential velocity, bringing that concept of tangential or linear movement, tangential velocity, meters per second, is equal to the radius about which something is rotating on a moving segment and the speed at which it's rotating, or the velocity, I should say, at which it's rotating, not speed, the velocity that it's rotating, radians per second, degrees per second. So let's put this in perspective. If the radius is set, you can't change the radius. You're not going to change the length of your arm when you're hitting a volleyball. You're not going to change the length of a bat. So if we increase the velocity at which something is rotating, that tangential velocity is going to increase as well. Another thing to think about too is, where are we striking objects at on a rotating body? You wouldn't want to hit a golf club up on the shaft you wouldn't want to hit a golf ball on the shaft of a golf club. It's not designed for that in the first place, and we know that that's a smaller radius. So no matter how fast you swing it, the linear velocity, meters per second of the head of the golf club is always going to be faster than the shaft. Same thing when you're hitting the volleyball. You're not going to hit a volleyball at your elbow. If we're looking at the entire arm from the shoulder to the hand, you want to strike the volleyball at the point furthest away from the shoulder, because it's going to be moving the fastest. And we know that force equals mass times acceleration. So if we have a set amount of mass, like the arm or the baseball bat or the golf club, and we need to accelerate it, and we know that acceleration involves velocity, we want to strike the ball at points that are furthest on these rotating objects, which could be a point on your body. So to bring that home a little bit, think about the points on your body that are going to be moving the fastest. Points that are furthest away from joints, hands, feet, because their radius is longer away. And if the angular velocity is the same, if the angular velocity isn't changing, it's constant, then we know that the velocity. Meters per second at the hand is always going to be faster than that at the elbow or even further up the arm. As far as units are concerned, angular versus linear units of measure in kinematics. Should say kinematics there. Sorry about that. Linear meters per second, meters per second squared, and then obviously you're just switching the units out, radians per second squared. So you can see where we're using radians. You could flip-flop out degrees there if you wanted to as well. Now we just take it one step further into acceleration. So you already know the relationship between velocity and acceleration from when we talked about it linearly. Same exact relationship here. The symbol that we're going to use to describe angular acceleration is alpha, or a cursive or italicized A. Degrees over second squared, or radians over second squared. Angular acceleration. Now, when we talked about linear acceleration, we talked about that there were two different components. Still the same here when we talk about angular acceleration. You can split it or resolve it into two perpendicular linear components. So now we're taking this rotating acceleration, this angular acceleration, and we're breaking it into two linear parts. One of those parts is going to be traveling across the circle, and one is going to be traveling in towards the inside of the circle. So if we take the tangential component, or the arrow that's traveling across the top of the circle in a tangent, or in line with the curve of the circle, we can describe that as that is linear velocity. That linear component of angular acceleration is linear velocity. You can see the equation there that describes it, v2 minus v1 over time. Now the radial component, which we'll talk about more in a second, is described as the velocity in towards the inside of the circle and the amount of time that takes. So we'll talk about that in more detail in a second. As a reminder, tangential component of angular acceleration is a straight line or plane that touches a curve or curved point. And when we talk about tangents, we're talking about a linear component. So we're taking this angular rotating body, something that's rotating in an angle, angular acceleration, we're breaking it into linear parts. So that first part is tangential. Its tangential is linear, linear is tangential, and that is linear velocity. So one component of angular acceleration is linear velocity, and that is the tangential component. It's directed along the tangent. It represents a change in linear velocity, or linear speed. How quickly is it changing? So when we're rotating around a circle, just imagine going around a curve in a car, running around a curve. You're on a bike and you're rotating around a curve, or your forearm is rotating around the elbow. There's two components to that. There's the straight line component, the linear velocity component. So if we're talking about the change and how quickly something is rotating, or angular velocity, or alpha. Alpha would be angular velocity. We're talking about that. We have to have a straight line component with the tangent, and then we also have to have a radial component. radial component to angular acceleration, or alpha. So this radial component is something that is a little bit trickier for people to understand. It's directed towards the center. So if my forearm is rotating around my elbow quickly, there's that straight line tangential component, the linear velocity component. And then if I'm still accelerating, there's this radial component. It's the amount of acceleration that's directed straight back towards my elbow, down my arm. Because my forearm is really easy to understand. My forearm is the radius. So the radial component of angular acceleration can be described as, now it's linear, right? Because we're breaking it into two linear parts, tangential and radial, and this radial part here is velocity of the radial component divided by the radius. So let's put this into a practical application. Why do we lean around a curve? Okay? Why do we lean around the curve? These sprinters are sprinting, they have angular acceleration, alpha. They are constantly changing their angular velocity, omega, omega 2 minus omega 1 over time. That's angular acceleration. So we know that their angular acceleration around this curve, it has a straight line component, that tangential component. That would just be their velocity straight ahead of them, the straight line speed that they're producing. But there's also that radial component. And that radial component is what keeps them on the curve. It's directed back towards the inside of the circle. Now we'll talk more about this in angular kinetics, but this angular acceleration towards the inside of the curve, for every action, there is an equal and opposite reaction. So there has to be an acceleration towards the inside of the curve, or if there wasn't a radial component, we would just go straight. This is the component that makes us go in a circle. But for every action, there is an equal and opposite reaction. So if there's a radial acceleration inwards, if you imagine someone, if you're standing on a rug and you accelerate the rug one way, your body's going to want to tip the opposite way. And again, we're going to talk about this more when we get to angular kinetics. But just understand that in order to stay on a curved path, you have to have this radial component of angular acceleration. And if it's moving inwards, our body is naturally going to want to float back outwards, because for every action there is an equal and opposite reaction. So in order for us to stay on our curved path, we lean. If Usain Bolt wasn't leaning, he would not accelerate in a curve. He wouldn't have angular acceleration if he didn't lean. He'd just go straight. He would only have tangential or linear acceleration. So for angular acceleration to occur, you have to have two linear parts working together. You have to have a straight line acceleration, tangential, velocity, and you also have to have radial component going inwards towards the circle. In order to combat the reaction from running in a circle, we have to lean. Or actually, to allow us to run in a circle, we have to lean. Let's practice. We've got the GOAT. Not so much the GOAT in 2019, but he's the GOAT no matter what, in my mind. His leg is swung for 0.3 seconds while accelerating at 200 degrees per second squared. What is the angular velocity of the leg around the hip? So our center of rotation here is the hip at the instant of the contact with the ball. Angular velocity has magnitude and direction. It is a vector component. If we knew that the measure of Adam's leg from hip to toe was 1 meter long, what other kinematic measure could we pursue? Now we have the measure of his leg. What else could we do with it now? Play around with this example. Think of any questions that you have. Don't forget to have fun.